Everybody have a calculator? You're gonna want one today. A lot of calculator work. Yep. Does not have to be a graphing one, but the other ones work as well. Okay. All right. So again, like I said, we're going to see how far we get today. My other class that I had for a full length, we did get to a very good starting or stopping point, but we did not finish the section. Okay. We're going to deal with exponential functions, which is going to deal with a lot of the exponent stuff that we've kind of already done. Okay. But then it's kind of more of an application of it. Okay. Today, what we're going to focus on is 3 different things: identifying information or functions as exponential or not exponential. We're going to begin to identify transformations of exponential functions. And then we're also going to be able to hopefully graph. You should be able to graph by the end of today. Okay. Transformations, that's a work in progress that we're going to do over probably 2 class periods. All right, let's go to the second page. If you're curious how I grade them, they're on that front page. Here's our first learning target. First learning target is I'm going to be able to identify functions that are exponential or not exponential. Okay, so here's the key thing. Exponential functions are going to be in this form: y equals a times b to the x power. Okay, here is the biggest hint that I can provide for you. Okay, as the x changes by a constant factor or a constant amount, the y is multiplied by a constant factor. That right there is the biggest indicator of whether a function is exponential or not. So you can look at a table and you're going to be able to tell if it's linear or, hopefully by the end of the day, exponential. All right, so what we're going to do is we're going to start looking at the x's. What's the pattern in the x's from 0 to 1, 1 to 2, 2 to 3? Doubling? 0 to 1, 1 to 2, 2 to 3? Going up by 1 every single time, just adding 1. That's awesome. That's exactly what we want to see. As the x changes by a constant amount, it's changing by a constant amount. Now, this is what I think you were saying. It's doubling, but is it? The first one's doubling, but is the second one? No, what's happening in the y's? Up by 2, adding 2. So let's look at what I have here. The y is multiplied by a constant factor. From one y to the next, am I multiplying by the same number every single time? Multiplying? No, I'm adding. This is not exponential. Okay, this is linear. As x's go up or down, I guess, by a certain amount, your y's are doing the same thing. They're going to be going up or down by a certain amount. That's what linear is going to be. We did do that in the first semester. I wouldn't blame you if you told me you don't 100% remember that. Okay, 1b. Let's look at the x's. Same thing. What's happening in the x's? Up by 1. That's a good thing. What about the y's? Let's check. 4 to 8. Is that timesing by 2? Okay. 8 to 16. Is that times by 2? 16 to 32. Is that times by 2? Sure is. Okay. So all of these is a times by 2 situation. This is a definition of what exponential is. This is exponential. As x's increase by 1, the y's are multiplied by 2. Okay. And it doesn't have to be exactly that. It could be as x is increased by 2, y's are multiplied by 4.8. That could still be exponential. Okay, so that's an example of what an exponential function is going to look like. Okay, now you don't. Right now, let's make sure we focus on the work and just identifying linear or exponential. Okay. So once you have those written down, why don't you try monitoring progress 1 and 2 on your own? And then we'll check it with me here in a second. Okay, so right below where it says monitoring progress 1 and 2, it's the same type of problem. Go ahead and give those a shot. Anybody think they're stuck on the first one? Is monitoring progress 1 exponential, linear? Maybe neither. Anybody think they know? What do you got?
Exponential,
How come?
because it's multiplying by 1/2.
Okay. I bet you a lot of you wrote divide by 2 here, right? 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. That's fine. You can write divide by 2. There's nothing wrong with that. But you do need to understand that dividing by 2 is the same as multiplying by 1/2. So the numbers can decrease and it still be exponential. Okay, and then the right one, x is increased by 1, y is decreased by 1. That's a linear function. Is there anything I can clarify on that little block? The example 1 block. So just what we did. Okay. When it comes to your test and it comes to your learning target, you're going to have problems like these. Okay, just like this. Okay. So if you need more help with those, I think there will be opportunity when we get to practice. That will not be in this class. That'll be in the next class. Okay. Let's go to the next one. Example 2A. Okay, so what we're going to do is we're going to evaluate. So it's giving me an x value. I'm going to plug that x value in, and then I'm going to figure out what number it is. That's it. Okay. I'm going to show you 2 different ways. I'm going to show you how you can do it by hand. Kind of do it in your mind and in your head. Then I'm also going to show you how you can just straight up type it in the calculator. I think we're at the point where we did so much exponent work. I'm content with you using technology to do that. Okay, so first off, y is equal to -2 times 5 to the 3rd power. So here's where my x is. My x is 3, so I'm plugging in x is 3. Okay, technically, and this is what your calculator's doing, it just doesn't tell you or show you. I don't know if you remember this guy. Technically, what it's doing is PEMDAS. Parentheses, nothing to deal with because 5 is simplified. Exponent, 3 or 5 to the 3rd power. Anybody happen to know what that is? 5 to the 3rd power. 5 times 5 times 5 again. 5 times 125. 5 quarters gives you how much money? 125. And then after I do my exponents, I do my multiplication or division, which would be -250. Yep, just watch out for those minus signs, okay? So what I just showed you is by hand. I think it's very beneficial to know how to do it by hand. Realistically, though, the vast majority of you're going to be way more successful with the calculator, okay? And so I'm going to show you exactly how to type it into the calculator. Here's how it goes. You're going to type -2, parentheses 5, caret symbol 3. This is exactly what it will look like. Okay, and I'm going to show you all where that's at right now, okay? Okay, and I know some people do get a little overwhelmed with these calculators because there's so much on there, but these are the type of calculators you can use on like your ACT, SAT if you take that, even the ALEX test maybe. I'm not 100% sure. So knowing how to use these are important, okay? So you turn it on with the on button down here. Okay, if you want to clear out anything that's in here, here's your clear button. Okay, we're going to type -2 first. There's a difference between minus and negative. Okay, so we're going to use -2. So -2, and then we're going to type our parentheses, which is right here. Parentheses 5. Okay, so that's what we have so far. And then here's your exponent button right here to the 3rd. And when you hit enter, it should just give you your answer, -250. Okay, so not too bad, right? Okay, now unfortunately, sometimes when that exponent's a fraction, you have to do a little bit extra work. So I'm going to show you. I'm going to do the monitoring progress with you all together. Okay, by hand first though. Y is equal to 2 times 9. And then I would replace the exponent with 1/2 because x is my exponent. It tells me it's 1/2. Okay, exponent. Anybody know how to find 9 to the 1/2 power? What number is that? So what root of 9?
1/9.
1/9. Nope. That'd be negative exponent. 1/2 exponent. That is 9. The what root of 9? I thought I heard somebody say it. The second root or the square root? What's the square root of 9? What number multiplied by itself gives you 9? 3. So this here would just end up being 2 times 3. So 2 times 3 is 6. And I'm going to show you exactly how to type that into the calculator. When you have to do, when your exponent is more than just a number, you're going to have to put parentheses around it. So this is how I would type this in the calculator. 2 parentheses 9 exponent parentheses 1 divided by 2. Okay, so you need to put the 1/2 in parentheses. And if you want to do 1/2 as a fraction, 1 divided by 2. Yes. 0.5 would work just fine. You're going to get the same answer. My question to you would be, how are you going to write 2/3? How long are you willing to hit 0.66666666666? So that's why I'm just showing you how to do the fraction. But 0.5 would work just fine. Okay, so let's see if we can do that. Okay, so go ahead, 2 parentheses 9 to the, and I have to do 1/2 as 1 divided by 2. 1 divided by 2. That's how I'm getting the 1/2. And it has to be in parentheses. When you hit enter, you should get your 6. Make sure the parentheses are around the 1/2. Yep. That's what you need to do is parentheses. Okay. All right, folks, we're going to do a heck of a lot of exactly that kind of on repeat. All right. But before we begin that, what I want to talk about is these functions are in the form y is equal to a times b to the x power generally. There's a little bit more that we're going to add to that. So when I look at this function, what do we think the a value is and what the b value is? What do we think my a value is and my b value is for this one here? What number's in the a position? What number's in the b position? -2 is a. 5 is B. Okay, what about for this one here? What's my A value? And what's my B value? Okay. We're going to deal a little bit with that, so it will be it'll just be necessary for kind of us moving forward. All right, let's go to the next page. Okay, this next page is a little bit more just discussion. Okay, what we're going to start progressing towards is being able to identify transformations of exponential functions. And then we're also going to be able to start graphing here. Okay, the first thing I would like you to do is I want you to bold in that middle line, and we're going to call that the x-axis. The y-axis is kind of already there. And what I'm going to do is I'm going to sketch you some exponential functions with just some important parts. Okay, what I want to talk about first is when the A value is positive, I want to talk about what does the graph look like when the A value is positive and the B value is greater than 1. This is what it's going to look like, generally speaking. Okay, this is going to be what we call an exponential growth function. And what makes it a growth one is the fact that the B value is greater than 1. That makes it growth. Okay, what I want to talk about here, this is a weird new concept. All right, so what's happening as I go to the right? Let's say that the growth factor is 2. What's happening is every time I go to the right, I'm doubling. If every time I go to the right one, let's say I'm doubling. So I'm multiplying by 2, I'm multiplying by 2, multiplying by 2. But as I go to the left, that means I'm dividing by 2. Constantly dividing by 2 as I go to the left. Okay, imagine I have a candy bar. And what I do is I cut it in half. I have half candy bar, right? And then I cut it in half again. And then I cut it in half again. And I cut it in half again. And I just continuously cut it in half. At what point do I literally have 0 candy? If all I do is cut it in half. How many times do I have to cut it in half before I have 0? Okay, let's say it is a regular size candy bar. How many times do I have to cut it in half to have 0? Let's pretend that I have like a microscope and I can zoom in and I have a little X-Acto knife and I can just, no matter how small it is, I'm just going and cutting it in half. We're getting on to something. I can always zoom in and I can always get smaller and smaller and smaller and smaller. So how many times is it going to take me to get to 0? Never. It will never happen. So this creates a weird little concept here. I think I'm spelling this right. I may not be. It's creating this thing called a horizontal asymptote. What that means is when I'm constantly just cutting in half or in thirds or in fourths, whatever it may be, I'm always cutting a portion of it out, but I'm also leaving a part of it behind. So what that means is I'm going to get infinitely closer to the x-axis without ever touching it and without ever crossing it. It's going to get infinitely closer, and it's going to create a horizontal asymptote. Now, off to the right is going to go up into infinity. But off to the left, I'm going to get infinitely closer to the x-axis. Okay, kind of same thing. Now what I'm going to do is I'm going to sketch when the a value is negative, but the b value is going to stay greater than 1. Okay, it is once again going to have a horizontal asymptote at the x-axis, meaning it's going to get infinitely closer to it, but never actually touch across it. And then it's going to grow exponentially off the graph. So it's the same thing. It's just going to flip over the x-axis. Okay. All right. So we talked about when b is greater than 1. Let's talk about when b is in between 1 and 0. When your b value is in between 0 and 1, our function is no longer a growth function, but rather it's a decay function. Okay. And so then here, what the graph does is it just kind of flips around. Okay. And so now this one starts high on the left and ends low on the right. With once again another horizontal asymptote happening at the x-axis. And this is me doing my best guess. I don't have it written down in front of me. I think it's spelled asymptote. Asymptote. I think the P is silent. Okay. Okay, now we're going to talk about when the a value is negative, but the b value still stays in between 0 and 1. Right, it's going to do the same thing the other graph does, and that's just going to flip it over that asymptote. Kind of just approaching infinitely that x-axis. All right. Things that are exponential growth. Money in a bank account would be exponential growth. Bacteria is exponential growth. When we had the COVID lockdown, your COVID cases was exponential growth. Decay, radioactive materials. It's the radioactiveness of it decays exponentially. A car's value, like unless it's a collectible car, the car is going to decay, or its price will decay exponentially. All right. So now what we're going to do is actually graph these. Do you need something from the top?
Yeah.
I'll get this back to some people here, but let's just keep moving. Okay. What we're going to do now is we're going to start graphing. Okay. So, what we're going to do though is we're going to learn how to graph and learn some of the transformations like on the fly. Okay. So we're going to do our best. Okay. This is the function that we're going to be responsible to graph. When it comes to the problems you'll have to do, you will not have to do this parent function part. We're doing the parent function part so we can learn to graph and learn the transformations at the same time. Okay, so if I have y, remember all of these are in this form. Y is equal to a times b to the x power. Your parent function will be in this form. Y is equal to b to the x power. It's just going to shed everything else away. And this is the one that you compare everything to. So the parent function of y equals 4 times 2 to the x power is what? Y equals. Notice that the only difference is it just gets rid of the a value. What? Y equals what? So look at this one here. What's its a value? What's its b value? What's the only thing that goes away? The a value. So just the 4 goes away. So the parent function is just 2 to the x power, okay? Okay, and we're going to graph this. For the most part, these are always going to be your x values. They do change, but we have not crossed that bridge yet. Okay, and if I want to find the y values that go with it, it's pretty easy. Because you have a calculator that's going to do most of the work. So here, x is -2, 1, -1, 0, 1, and 2. So I'm going to start by taking my calculator, and I'm going to clear out what's in there, and I'm going to go 2 to the, and then my first x value is -2. So my first y value is 0.25. Okay, then I'm going to do the same thing, but instead of -2, it's going to be -1 now. 0.5. Same thing. 1. 2 to the first power. It's 2. And then the next one, 2 to the second power. So now I'm going to try to plot these to the best of my ability. Negative 2.25 is pretty close to the x-axis. Negative 1 and then 0.5, that's right in between 0 and 1. 0, 1. 1, 2. 2, 4. And so that's a nice little sketch of what this graph will look like. Okay, questions about that? Let's do the one that we're actually tasked to do. Okay, we're going to pick the same x values. And now what we're going to do is we're going to graph this, but now I have that 4 in the front. So now I'm going to go ahead and graph that with the 4 included now. So this is going to be 1. 4 times 2 to the negative first power is 2. So the 0 power is 4. To the first power, 8. To the second power, 16. So negative 2, 1. Negative 1, 2. 0, 4. 1, 8. 2, 16. Folks, I just killed it on those two graphs. Those are good looking. Okay. The point of us doing the red graph is so we can see what impact does this 4 have, an A value of 4 have on this red one. So from red graph to black graph, what's happening? Red graph to black graph. What's happening? Okay, so it would have been bigger then because red to black. It's getting bigger to some extent. Which way? Which way is it getting bigger? Wider, taller. Taller. So vertically, it's changing. Okay. So what I would call this, if I'm going to put a formal name with it, if it's vertically getting taller, okay, this is what I would call a vertical stretch. So this, from the red graph to the black graph, that 4 as an A value stretches the graph vertically. Okay. And that vertical stretch has a scale factor. Let's figure out what that scale factor is. I can figure out that scale factor by looking at my Y values. Red to black. Red to black. 0.25 to 1. 0.5 to 2. 1 to 4. 2 to 8. 4 to 16. What's it being scaled by? What number? What number is it getting scaled up by? Two, if it was going two, wouldn't I have from 1 to 2 though? Because 1 times 2 is 2, but I have 1 to 4. It's not doubling because that would be multiplying by 2. What's the scale factor if I'm going from 4 multiplied by what number is 16? 4. And what's my A value? So that scale factor is 4. Okay, this is what I want us to do between now and lunch. It's going to be pretty short. I'm going to give you the parent function. I'll show you how to do the first one, and I want you to try to graph that before you leave. Your parent function is just the b value raised to the x power. Okay, so this is your parent function of this one. Okay, and this is how you do it. You just have to put that 1/4 in parentheses. So that 1/4 to the negative second power, that's going to give me 16. Okay, so what I would like everybody to do between now and lunch is try to finish up this parent function. And then at that point, you have a little break until we go to lunch, okay? Which is only a couple minutes, but it is what it is.